Okay, good afternoon. I'm Steve Sparks, the president of the VGP section, and it's a great pleasure this afternoon to hear about the lectures of the Bowen awardees and, of course, honour them for their great achievements. And we've got two Bowen Award lectures this afternoon, the first to be given by Marc Hirschmann. And perhaps I could invite Marc to come and join me on the podium. Marc has been awarded the Bowen Award for the insightful and creative application of thermodynamic and experimental investigations of melting of a lithologically heterogeneous mantle, for careful elucidation of the influence of volatiles on peridotite melting, and for development of melts program to predict the nature of low degree partial melts of the mantle. So I'd like to first of all give Marc, for his achievements, a certificate for the lecture. Marc will be getting, and Jamie Connolly too, will be getting the awards this evening at the VGP reception, so please don't miss that. That'll be a great event. But first of all, I'd like to congratulate Marc and give him the certificate for his lecture.
Well, thank you, Steve. Two certificates. Wow. First, I have to say that there's some of you who might have seen a talk, you may think you've seen a talk similar to this at the Goldschmidt this past August. There definitely will be similarities. On the other hand, I think most people who were at Prague in August had such fun that they probably don't remember the details of any of the talks that they went to, so I'm sure it's worthwhile hearing it again. In addition, at that talk in August, I ended it with a prediction, and now I have some data that may help us evaluate that prediction. So there's something for those of you who think you might be having some sort of deja vu experience. Pointer. The first thing I want to do is I want to kind of explain this title, By Permission of the Mantle. It's something that some of you have heard me say before, but I'll say it over and over again until people stop me. Everything that we hold dear, the biosphere, the climate, all the water, all the stuff on the surface of the Earth that are volatiles really exist by permission of the mantle. It's the stuff that the mantle either didn't want or wouldn't take back. And in fact, you may think that that's just the way it has to be, but when one considers how planets may evolve and the different chemistry of planets, it really doesn't necessarily have to be so. You could need only change the stability of hydrated silicates by a few hundred degrees, and it would be very difficult to have large amounts of surface water. You could have a very reduced mantle in which all the carbon wants to go into the core or stay in the mantle, and you would have trouble running a greenhouse over billions of years. And in fact, our sister planet Mars may have suffered from exactly that fate. So really everything about our blue planet with the nice biosphere is by permission of the mantle. Oh, no? What do I do? Do I just... I don't want to do that. I can do that. Okay, so the topic of the talk, there has to be a better way than that. The topic of the talk is about volatile cycles, and I want to tell you about why volatile cycles are important, because I'm sure some of you aren't really convinced. Okay. Really. I would make the case that the fact that there are volatiles cycling in and out of the mantle on hundreds of millions to billions of years, billion-year timescales, is a significant contribution to almost everything that people in this room care about on some level. A really good example of that is plate tectonics, right? It's probably the best example of that. We know that the style of convection in the mantle today is dominated by plate tectonics, which in turn has a particular style of deformation near the surface where there's a very soft region, which we call the asthenosphere. The existence of the asthenosphere depends on not just the properties of solid material, but also how that material is affected by volatiles, whether it be because the effect of water on the flow properties of mantle, or perhaps because there's small amounts of water or carbon-rich melt in the mantle. one interesting thing that I think is a challenge for all of us is to say it's true that volatiles are important to the operation of plate tectonics. It's also obviously true that plate tectonics is key for the cycling of volatiles. And if we think back in terms of the history of the Earth, we actually don't know which of those comes first. We don't know whether or not volatile cycling allowed plate tectonics to happen, or whether or not plate tectonics is the reason that volatile cycles have operated so effectively on our planet. Okay, and before I continue with my talk, I want to make a digression. It may seem like a very big digression. About 30 years ago, isotope geochemists hatched this wonderful thing called chemical geodynamics. Chemical geodynamics is the idea that we can understand the dynamics of our planet and the history of the dynamics of our planet through isotopic tracers. One can use the geochemistry to understand the dynamics. Well, when we talk about volatile cycles, we're talking about something that I think is even better than that, right? It's another kind of chemical geodynamics in which not only is the chemistry tracing the history of the dynamics, but the chemistry is also affecting the dynamics. There's a feedback between the concentrations of volatiles in the different reservoirs and the dynamics of convection, which in turn affects the chemistry. So deep earth volatile cycles are a new form of chemical geodynamics with that much more interaction. Now, I should also say, when we think about, well, the chemistry affects the physics and the physics affects the chemistry and so on, maybe not on this scale, but you know, there's another word for that. It's called petrology. So something else that is going to be very important in this lecture is that this is the modern Earth, and we have deep Earth volatile cycling that's happening here, an operation of plate tectonics. This is the ancient Earth, which had all kinds of very interesting things, including delivery and storage and influence of volatiles in many different ways. And one very serious question that I have is the extent to which this modern Earth descends from this ancient Earth. To what extent does the Earth today depend on the initial conditions of that volatile delivery as well as the other energetic influences that occurred then? Okay, so here we are with modern deep volatile cycles. I've actually haven't really described what they are. I've just assumed that you all know. But the key thing, of course, is that for hydrogen and carbon and probably a lot of other things, there's this large surface reservoir. That surface reservoir comes from volcanic emissions, chiefly at ridges and elsewhere. It also goes back to some extent or another into the mantle, chiefly by subduction. And we understand the water cycle reasonably, well, not well, but we have some understanding of it because people have been working on it for about 20 years. The carbon cycle is newer in our perceptions, and there's less that we know about it. But I would say that we don't really know too much about either of them. Okay, so I just put in a plug for petrology, but let's go back to geochemistry. What does a geochemist do when a geochemist has two things that he or she sort of understands, or maybe not? Make a ratio, that's right. So one really interesting way to approach this is to look at the relative effectiveness of the water and the and carbon deep earth cycles. And this is something that we did a couple of years ago. And one very interesting result about it is that if one looks not at the deep obscure things, but just the hydrogen and carbon that exist on the surface that are easy to inventory, you end up with a hydrogen-carbon ratio that I think is very, very interesting. It's remarkably high. And I'll show you this, and I'll tell you why I think that's interesting, actually, for the rest of my lecture. So inventorying the water on the planet is really easy. It's just the oceans, right? So you add everything else, and it's just a small adjustment. The amount of water that's existed on the surface, this is a bit of a controversial thing, whether or not the volume of the surface, or excuse me, the volume of the oceans has been constant through time. Certainly through the Phanerozoic, the change has been very, very small. Sea level changes of a few hundred meters are just a few percent total change in terms of the total surface inventory. Whether or not that goes all the way back into the Precambrian or indeed into the Hadean, I would reserve judgment on, except to say that even if it has changed a little bit, it hasn't changed dramatically. We've had shallow water sediments on continents for as far back as we can see. We know less about the history of the carbon cycle, but it's actually fairly easy to inventory at least the modern carbon fraction of in the exosphere. It's dominated by continental sediments. So this I've taken from Sleep and Zonley, but one can look at a number of different places where people have done this sort of inventory. People get more or less the same numbers. You take the mass ratio of hydrogen and carbon present day, and you get this number that's basically about 2. Okay, there's twice as much hydrogen in the exosphere as there is in carbon. The reason that this is interesting is because this ratio is significantly higher than the ratio in the mantle. Right? If we look at any kind of record that we can see from undegassed basalts or melt inclusions and so on, and that's what all this stuff is here, the hydrogen-carbon ratio of the interior is much lower than that of the exterior. The operation of the deep earth water cycle has put more water on the surface than carbon for some reason, or alternatively that the mantle has kept the carbon. Why? It's not really obvious why that is. So here are some possible considerations. The first thing you might think is volcanic outgassing, but that actually has the opposite effect. Carbon is more incompatible than hydrogen. It should put more carbon onto the surface relative to hydrogen. If you want to think about loss of volatiles to space under normal conditions, normally hydrogen escape is much, much more efficient than carbon escape if there can be escape at all. So those two don't work. So we're left with another set of possibilities. One, which is one that I thought was the answer for some time, and I'm going to make the case, and then I'm going to tell you why I have my doubts about it. And that's simply that through the operation of plate tectonics, there's been preferential subduction of carbon, leaving behind a fractionated reservoir on the surface, a high hydrogen-carbon ratio. And then the other, which I think are even more interesting, is that, in fact, this is that the Earth remembers early events from the very first basically crystallization of the magma ocean or impacts therefrom, or from that era anyway. And that despite our sort of idea that plate tectonics rules everything, the way that volatiles work on the surface is really a remnant of the very beginning, from the initial condition. Okay, so these are some experiments that Raj Dasgupta did a number of years ago when he was at Minnesota, looking at partial melting of carbonated eclogite. One of the reasons that we were interested in this is to determine how ultimately carbon may or may not subduct along various geotherms. There is, of course, metamorphic devolatilization, but that doesn't take away all of the carbon during subduction. So whether or not subduction effectively flushes the carbon back to the arc or takes it for the ride into the deep mantle depends on the position of the solidus. And what you can see is that, at least in the modern times, carbon subducts, except for perhaps Cascadia or really, really hot subduction. But for the most part, it does. So operate that for billions of years. There's, of course, a certain amount of hydrogen subduction, but if it's less efficient, then you can explain exactly what it is that we see in this hydrogen-carbon ratio. So that would be this. The water reservoir hasn't changed appreciably. Carbon is being drawn down by subduction, and the exosphere hydrogen-carbon ratio is slowly going up through time. That's possible, but like I said, I have my doubts. I have my doubts actually for three reasons. The first one is more and more complicated. The first one is more and more complicated as I think about it, so I'll tell you a little bit about it. Of course, these are modern subduction temperature depth paths compared to the solidus of carbonated eclogite. What we want to be concerned with is not what's happened recently or even in the last 500,000 years, but through 4.5 billion years of history. And am I sort of tuning in and out, or is this okay? Okay. I guess as I turn my head, it changes a bit. When we look back in time, we see fairly little evidence more than 1 billion years ago for metamorphic belts that look like modern subduction zones. And this has been a topic of considerable discussion amongst metamorphic petrologists and people interested in the Precambrian. These would be metamorphic gradients that look like blue schist. You go back about 1 billion years and they're gone. Mike Brown, from whom I took this figure, has argued that that meant that the subduction was at a hotter temperature in the past, and these so-called eclogite high-pressure granulite facies were the sort of the Proterozoic or the Archean equivalent of subduction. But if you take these gradients and apply them to basically the carbonated eclogite solidus, they plot over here, and you can see very strongly that if they apply, that slabs should have decarbonated up until at least first 3.5 billion years of Earth history. It's very hard to generate this extreme fractionation of the surface reservoir this way if carbon has only subducted in the last 1 billion years. On the other hand, I'm not sure that everybody is convinced that these are subduction geotherms. Perhaps subduction didn't operate in the same way, or perhaps if it did, we don't have a record of it any longer. I presented this actually at Prague, and Peter Van Kecken pointed out to me that he doesn't think that these kinds of subduction, or these kind of geotherms can be subduction geotherms, and to prove that, he ran one of his models with extreme temperature and also with very shallow decoupling, and he just barely touches into these fields. So another interpretation is that these metamorphic belts aren't associated with subduction at all, and again, either there was no subduction or there was, and we don't have a record of it in any metamorphic belts that are preserved. Okay, so it's possible that it wasn't, subduction of carbon didn't happen earlier in Earth history. That's one possible objection to this idea. The other one, it comes from the sedimentary record. And that is that as one goes back in time, the abundance of carbonates in sedimentary sections gets smaller and smaller. And that's shown in this diagram here, where we have limestones and dolomites and so forth. They're important in the last billion or billion and a half years, but as one goes back, sedimentary sections are effectively devoid. People who work on this assume that the carbon reservoir, the surface reservoir, has actually grown with time as more and more carbonate has been stored on the continents, that it has something, that it has a path, something like that. Well, that's actually the direct opposite of what we were hoping to see, right? We were hoping to see that the carbon would slowly be drawn down as more and more of it was subducted. And so if the water reservoir is approximately, if it's steady or if it's going down a little bit or going up a little bit, but the carbon reservoir is growing gigantically, then you don't have any way to develop a high hydrogen carbon exosphere value unless, of course, you started with an even more extreme one. Makes our problem worse, not better. And finally, my third objection, or at least objection may not be the right word, the third reason why I hesitate to say that this is all a product of subduction is the record of carbon isotopes, which do not show any long-term secular evolution through time on Earth. If we were subducting carbonate through time, and putting a significant fraction of what was once on the surface back into the interior, you might expect to see a signal, both actually in the surface carbon reservoir in terms of carbon isotopes of surface materials, but also in the Mantle reservoir as recorded in the ancient with diamonds and in the modern with basalts. And perhaps there's a record there that we haven't actually divined, but for the moment it doesn't seem like there's such a record. There are ways to get around this perhaps, but it would be interesting to see if we could explain this lack of secular evolution with a model that basically says there used to be 3 or 4 times more carbon on the surface than there is now, and it's all been subducted. Okay, so preferential subduction of carbon isn't dead. I'm just saying that I have my doubts. So what I'd like to do now is to discuss the possibility that this fractionation is actually telling us that the Earth's deep Earth volatile cycles are still very much dependent on something approximating initial conditions. And there are 3 of these. I'm actually going to spend most of my time on the third one, but I briefly will go through these 2. Okay. So again, I just want to emphasize the point that what we're considering is that there was an early Earth that was just very, very different in every respect from the modern Earth, and that the modern Earth emerged from this in a way that perhaps set the stage for a great deal of its further dynamical and geochemical development. So one possibility is, I said at the outset that normally hydrogen is lost from the atmosphere or lost to space preferentially from carbon. But I can think of one scenario in which that may not be the case. And that scenario would require something very special. And that would be if you imagine that an early Earth had a very thick CO2 atmosphere, something like Venus has today, hundreds of bars of CO2, which would be a significant fraction of the Earth's total carbon budget, and that at the same time it also had an ocean, and that it went through a giant impact, something like the moon-forming impact, then, in fact, numbers of simulations of this scenario have the atmosphere escaping with essentially no escape of the atmosphere, leaving behind a carbon-poor, thin atmosphere and a huge amount of water still. And these are simulations by Genda and Abe from a few years ago. This is the amount of % of atmosphere loss for different impact simulations. This is percent of ocean loss, and you can see that the ocean loss doesn't even begin until the atmosphere loss is 100%. Now, that's probably too simple a model, but the point still is that there are simulations for which large amounts of atmospheric loss result and negligible amounts of ocean loss occur through this impact. And this would be the magnitude of a Mars-sized impactor. So it's quite plausible that this is the answer. Unfortunately, there's very little way to do any petrology on this problem. Okay. This one, is it not in my slides? It's not. Okay. I'll just tell you about this one briefly. It's Norm Sleep and Kevin Zonley's idea that basically the early Earth was littered with glass beads, a lot like the lunar surfaces because of all the impacts. Glass beads love to react with carbon in the weathering environment, and that by some magical way, that veneer of highly altered glass beads full of CO2 made as carbonate, subducted in a dynamic environment over a short period of time and has never been seen again. Not necessarily so testable, but I could be right. Okay, so what I'm going to do is I'm going to spend the rest of my time on this one here. So consider a magma ocean, right? Magma oceans are fairly dynamic environments. We certainly believe that they convect vigorously. Also, presumably, God only knows what the atmosphere above a magma ocean is in terms of its weather and its hurricanes and so on. But starting at a couple thousand degrees at its base, it will have a tremendous amount of vigor and a great opportunity as long as this boundary remains open. In other words, as long as you don't get like an anorthosite crust on it or something like that, for exchange between the two. And the solubility, of course, of water and CO2 are differential in a magma ocean, and the water solubility is marginal, so you get a certain amount of water dissolved in the magma ocean, and the solubility of CO2 is much less. So you get, in this case, to whatever depth the planet is molten, you get almost all of the carbon on the surface from this process. And that just looks like this, just showing you what's very well known. The water solubility is substantial. The CO2 solubility at low pressures is very, very low. So the initial condition that we might expect in this most simple-minded way to think about how volatiles behave in a magma ocean is that you have an atmosphere with a huge amount of CO2, a smaller amount of steam, compared to a magma ocean in which the opposite is the case. And then, of course, you have the crystallizing silicates, which take a certain amount of water, and the nominally anhydrous silicates take almost no carbon. And you develop a mantle with super high hydrogen carbon and an atmosphere that's left behind with very low hydrogen carbon. Right? That's exactly the opposite of what we have today. So you may be thinking, why do I want to appeal to a magma ocean to give us the opposite relationship? Okay, well, we will get there. Oh, it's there. I see. It was just out of order. Okay, so these are the lunar glass beads, and this is the model of Sleep and Zonley, which shows all the carbon on the surface because it goes into the CO2 atmosphere after crystallization of the magma ocean, and then an immediate plunge, and then a build back up as the sedimentary record on the continents build itself. Okay, and that looks like that. Okay, sorry about that. Okay. Well, what I just told you is that initially the magma ocean would want to put almost all the carbon into the overlying atmosphere, and there'd be vigorous exchange between the two. But what I'd like to speculate about is the possibility that the magma ocean may actually function as a carbon pump. And if it functions as a carbon pump, that it may precipitate carbon in the crystallizing phases as something like diamond or carbide or alloy, which means that the carbon is taken out of the magma here. You have carbon-depleted materials that rise up to the atmosphere. They replenish themselves with this maybe 100 bars of CO2 pressure, go back down and so forth. And in so doing, the crystallizing magma ocean may in fact put a very large amount of the carbon that was initially in the atmosphere into the solidifying mantle, creating an atmosphere that's not nearly as thick and creating a proto-mantle, if you will, that has pretty much all of the carbon on the planet. The reason for speculating about this has to do with the influence of FO2 on solubility of carbonate. Right? We can look at the solubility of carbonate as a function of pressure, and of course it varies a lot, but what really affects the solubility of carbonate is the FO2. Because under reduced conditions, carbonate isn't stable. Instead, a solid phase, graphite or at greater pressure, diamond or some other reduced carbon is stable. And so what we can see here is that along the peridotite solidus, as a function of FO2, where we might have this 1,000 ppm, graphite saturated 0.1 weight% under fairly oxidized conditions, the solubility plummets to less than a part per million under reduced conditions. And remember, iron wustite -1 or iron wustite -2 is about the condition of equilibration with, or potential equilibration with the core, equilibrium of a silicate liquid with 9 weight% iron and with metal puts us somewhere in here. So what if the surface conditions were this and the deep conditions were this? There would be some solubility of carbon at the surface, and then that material would go down and hit that reduction front and precipitate. Is this a good idea? Well, all right. And while we consider it, we also want to think about what we're talking about with respect to the atmosphere as well, right? Because all this time I've been talking about an atmosphere of H2O and CO2. And is that right? There's a long history, it's more than half a century old, about speculation about Earth's earliest atmosphere. And the pendulum has swung back and forth. Right? Originally, it was Miller and Urey looking at the atmosphere of Jupiter as an analogy to the earliest atmosphere. And they assumed that there was no CO2. It was methane and ammonia and hydrogen and so forth. And of course, this is really important because this is the kind of atmosphere that's been shown to be very conducive to prebiotic chemistry. And so whether or not one has an atmosphere like this, that's kind of important for the origin of life. It's also important for the preservation of the atmosphere. These molecules are not stable in the atmosphere over long periods of time, and an atmosphere like this has greater propensity for atmospheric escape. More recently, people have assumed that the early atmosphere is water or CO2, either because they think it came from comets or by analogy to modern volcanoes, which don't degas this sort of stuff. They degas this kind of stuff. And so it's become more popular to assume that this initial atmosphere was water and CO2. Yet more recently, people have thought about the dynamics of this a little bit and thought about delivery of volatiles from impactors, which they assume are like chondritic meteorites. So if you just do the thermodynamic calculation and cook up a chondritic meteorite and see what kind of vapor species are going to come off of it, you see species like this, which are, of course, very similar to species like this. And so the pendulum has swung back, and now it has become more popular to say that this early atmosphere, this impact-generated atmosphere, is reduced. Interestingly, this is just a paper from last week, looking at oxygen fugacity by looking at the Jack Hill zircons. And it does appear, as early as we can look back, that these zircons, which come from crustal rocks, which may or may not remember the mantle, are relatively normal in their oxygen fugacity. They're around FMQ. So going as far back as we can look in the rock record, we don't see a lot of evidence of this early reduced Earth. If it existed initially, it didn't. Early reduced surface conditions on the Earth. If it existed initially, it didn't persist very long. Okay, actually I want to step back here for a moment. So once we start considering this, once we start considering the conditions of whether this is CO2 or CH4 chiefly, then we have the ability to consider not just, well, the atmosphere was delivered by comets or the atmosphere was delivered by chondrites, but instead that there are tens of thousands or hundreds of thousands of years of this reservoir interacting with a very, very large redox buffer, if you will. I don't mean that in the formal sense, but I mean it in the sense that it has a great deal of redox capacity. And I would submit that the magma ocean is going to determine what the oxygen fugacity is of the overlying atmosphere. Just in terms of numbers of electrons, this wins by many orders of magnitude. So this atmosphere-magma exchange is probably what's going to determine what the composition of the atmosphere is following the event of the crystallization of the magma ocean. Okay, so the way I would like to think about this is this. It's very simplified, I admit, but it's a starting place. Imagine that the magma ocean has metal in it, or even if it doesn't have metal in it, it recently had metal in it and it has recently lost that to core formation. The bottom of the magma ocean remembers equilibration with metal, right? So that sets the the oxidation state at the base of the magma ocean as whatever is necessary for the magma to be in equilibrium with iron metal. It's convecting vigorously, and what that means is that the composition is constant, so the carrier of oxygen fugacity in the magma ocean is the ratio of ferric iron to total iron, which should be approximately homogeneous. And what that means is that the oxidation state at this interface, which is going to set what's going on in the atmosphere, is set by this value here. However, just because conditions are reduced here does not mean conditions are reduced here, because the pressures are very, very different, right? The people who are working on siderophile element chemistry, for example, keep making this boundary deeper and deeper. 25 GPa a number of years ago, 50 GPa, 80 GPa, very high pressure, any of those numbers. Right? So the fact that these are very different pressures but the same composition means what we need to know is what's the FO2 gradient in this magma column, if you will, at constant ferric iron to total iron. If we take the data that we know about from low pressure, this is what we would conclude. Right? This is the work of Crust and Carmichael, or a more recent paper by Hugh O'Neill et al., taking the measurements that they've made in Crust and Carmichael, their sound velocity measurements at 1 atmosphere. In O'Neill et al., they are high-pressure experiments up to about 3 GPa. And we would conclude that at constant FO2, at least at a constant buffer, the ferric iron content diminishes with increasing pressure, which means that if we take something that is at a certain oxidation state at high pressure and decompress it, it becomes even more reduced. So, if core formation is here, the conditions at the surface are unbelievably reduced, if this is correct, or if this applies through the magma ocean. So that's this, right? So iron metal here, this is iron wustite minus 1.5. This is iron wustite minus God knows what, right? And the atmosphere above this has got to be basically all hydrogen. But that's not the only possibility. The other possibility is that this trend of oxidation with depth in a self-compressed magma actually doesn't continue, that it's only a low-pressure phenomenon, and that at high pressure, the opposite begins, and that one can have fairly reduced conditions at the surface, at depth, and oxidized conditions at the surface, such that even though there's metal here, the initial atmosphere could be basically a water CO2 atmosphere, the kind of atmosphere that would exist for the kind of QFM conditions that the crust records in Jack Hill zircons just a couple 100 million years later. Okay, so I'm now going to speculate, as I did in Prague, that this is actually the right one. And the reason I say this is that this relationship of oxidation with depth in self-compressed magma that we get from the thermodynamics of silicate liquids at low pressure is the direct opposite of what we believe is the case for self-compression of solid peridotite. Solid peridotite of a given composition with increasing pressure becomes more and more reduced. This is why many people have been talking about reduced conditions and even iron precipitation in the transition zone and the lower mantle today. So the fact that this is the opposite may lead us to ask why, and the reason is that with increasing pressure in solid mantle, the conditions become more reduced as ferric iron becomes more and more stable in high coordination sites that are made by the high pressure minerals such as garnet and transition zone phases, majorite, wadleyite, and so forth. Right. So this trend here in the solid mantle of reduction with increasing depth is the opposite of what we get from low pressure. Notice the difference in scale here in the molten mantle. Wouldn't be too surprising, right, if with increasing pressure, ferric iron began to take on higher coordination states in silicate liquids. After all, that happens in lots of other cations that we know about, like aluminum and so on. And that's shown here. This happens to be a simulation from Lars Sticksrud and company showing that with increasing pressure, actually read backwards on this scale, that silicate liquids take on higher and higher coordination states that kind of mimic the coordination states that one sees in the minerals that are stable at those pressures. So this stabilization of ferric iron with increasing pressure that one sees in minerals may also occur in melts. So in other words, if these curves turn around up over there in the corner, such that with increasing or with decompression from those, one ends up with very, very high ferric-ferrous ratios, even though the conditions are buffered by, say, coexistence with metal, then we would have the opposite relationship from the low pressure, and it would be possible, number one, to have an oxidized atmosphere, and it would be possible, number two, for the conditions of the carbon pump to be met, which would be taking the atmosphere and bringing it into dissolved silicate magma near the surface, with convection bringing it to the depth, and then precipitating it as a reduced phase, and putting most of Earth's carbon in the crystallizing mantle rather than the atmosphere. And these brand new experiments, some of you were there, but probably most of you missed it. I can't do a poster advertisement for a poster that's already happened, but this is my student Honglo Zhang, who presented this morning in the poster session. And these are experiments buffered by a metal oxide buffer as a function of pressure measured by Mossbauer spectroscopy. And we have to keep stepping up in temperature because we keep hitting the liquidus, but this is the low pressure prediction, which we see, and you can see it's beginning to turn up. Right? So if this trend continues, what we will have is exactly the conditions required for the carbon pump and required for an oxidized atmosphere following the crystallization of a magma ocean. Right? That would be this here. Okay, so I think that the earliest Earth perhaps was like this. Much of the carbon and the high hydrogen-carbon ratio of the surface as compared to the magma ocean may descend from this, and that in addition the conditions of kind of a thick CO2 greenhouse early in Earth history is at least plausible. Stay tuned for more data. Right? Just like that. Okay? I don't think anybody wants to read my conclusions. So, yeah. All right. No. Oh, wait a minute. Never mind. The last slide was supposed to be something pretty, but never mind. I'm done. Thank you. I can't see anything. If anybody's raising their hands, I have no idea.
I think, yes, we've got some time for some questions. So if you could raise your hand, I'll see if we can, people could go forward to the microphone there, because it's such a big room, to ask their questions.
Marc, right. How much carbon might you put into the core itself?
All of it? Actually, if you do the calculation, there's two ways to think about this. One is how much carbon can you put into the core just in terms of the phase equilibrium of the core. And then the other is how much carbon do you need to put into the core in order to really tweak the mass balances that we're talking about. The second question, when people talk about the light element in the core of weight percent, if the core has merely a few thousand parts per million carbon, that totally dominates the Earth's carbon budget. So in that respect, as much as one likes. In terms of the total solubility of carbon in carbide melts, I'm sure it's pressure dependent, but from the fairly low pressure data we have, it's on the order of 5 weight percent. But from my perspective, as much as it likes, if conditions were really reduced during core formation, and if there's carbon available, the core can take it all.
Microphone is close by. Have you included nitrogen?
No. Wonderful. It needs to be done.
Okay, thank you.
Marc, my question was going to be much in the same spirit. There's a whole bunch of other volatiles, the noble gases that would be very interesting, particularly xenon-129, for the very early history. And then I'm always intrigued by, what happened that initially gases were just lost almost immediately, but then argon, sort of, 50% of it supposedly is still down there. So somehow that must come into the story in some fashion.
Yeah, I haven't thought of any really nifty ways to invert the solubility of rare gases with pressure. But if that happens, then there could be all sorts of interesting similar effects. My guess is that they aren't, but yeah.
Any other questions?
All right. We adjourn for, I was fast.
Yes, I'll just, well, thanks very much for the great lecture, Marc. And as I just remind people again, there's the VGP's reception this evening, and everyone's welcome at 6:30, Salon 9 in the Marriott. and Marc will be receiving the Bowen Award at that meeting. So thanks again, Marc, and we'll reconvene at 5 o'clock for Jamie Connolly's Bowen lecture. I'll just introduce you, and then I'll invite you to come up. Okay, thanks very much for staying around for the second Bowen lecture, and it gives me great pleasure as VGP President to introduce Jamie Connolly, and he's cited for the Bowen Award for innovative and ingenious application of thermodynamics to phase petrology, including the development of the software package Purple X to perform these calculations, and for calculations of physical parameters and dynamics of crustal fluid flow. And he's going to tell us about hydromechanical model for fluid flow in the lower crust. So if I could invite Jamie to come to the podium. And so it gives me pleasure to give Jamie the certificate for the 2011 Bowen Lecturer Award. Well done, Jay.
Thank you, Steve. How does this? You'd think that somebody who's getting an award would have something new to talk about, but sort of like Marc apologized before for giving a talk that had already been given 1 year before, I have to apologize for giving the same talk that I've been giving for the last 15 years. And actually, unlike Marc, mine is exactly the same pretty much, but I had to remember what it was this time. And what this is basically is my attempt to, as a metamorphic petrologist, the way I understood that the way fluid flow is supposed to take place in the lower crust, to try and reconcile this with some elementary mechanical concepts, to try and make a consistent model. So to start with, what is the process that I'm talking about? Pretty much everybody acknowledges or believes that the primary source of lower crustal fluids is devolatilization metamorphism. And what is less appreciated about this process is that it generates a pervasive grain scale porosity. So you could imagine that after a metamorphic reaction, we have a region of fluid-filled porosity surrounded by relatively compact, unreacted rocks. What happens next depends on either when or how you are educated. The classical metamorphic school holds that rocks have absolutely no strength. In that case, the rocks overlying the metamorphic reaction front act like a permeable piston that literally compacts out the porosity and drives the fluid upwards. And that would be a purely compaction-driven fluid flow. And the problem with that particular model is that as time has gone on, metamorphic petrologists have developed more and more sophisticated tools to track fluid flow during metamorphism, and they find that fluids flow in all different directions rather than just vertically. So to sort of accommodate this observation, a second school of thought has developed, which I've dubbed the modern school. And in this school holds that rocks are completely rigid, or possibly rigid plus brittle. And the important thing to understand about this kind of model, which is basically the type of model that people use in the upper crust, is that if the rock skeleton is rigid, it can't transmit its information about stress state to the fluid phase. So very small very small pressure perturbations within the pore fluid are what are actually responsible for driving fluid flow. So you can get these very small perturbations can drive all sorts of exotic fluid flow patterns. And while some of the fluid may by accident get to the surface, fundamentally these are models for circulation. And the deficiency in these models is they cannot explain metamorphic fluid expulsion. Now the people who use these models, I don't think anybody's denying that compaction really occurs. What's implicit in the use of these models is simply they're assuming that the timescale for compaction is much, much greater than the timescale for fluid flow. Okay, so 15 years ago, I began working on this problem. And what I wanted to do was consider the case someplace between these scenarios where rocks had finite strength. And the intriguing phenomena that emerges from that, which people knew already when I started, was that the fluid flow is accomplished by the propagation of domains of fluid-filled porosity, or porosity waves. And these porosity wave solutions seem very ungeological to people. So what I would like to sort of devote this talk to is trying to justify the assumptions that lead to these models and spend a little more time than I usually do trying to outline what I think the initial conditions for these porosity waves might look like. So, to my beloved assumptions. I just realized, I was just informed that this font is completely illegible at the back of the room, so my apologies. But the universal assumption that drives all phase petrology is that fluid pressure equals total pressure. That assumption, if you look at phase petrology itself, the argument is largely circular. I don't think you can really say from phase petrology that this assumption is true. The assumption is completely inconsistent with lateral fluid flow, which metamorphic petrologists are very fond of. But there is evidence from deformation style, that is both geophysically and structurally, and from fluid inclusion studies that does support that although fluid pressure may not be lithostatic, it is certainly above hydrostatic conditions. And from a mechanical perspective, that is from the perspective of somebody interested in compaction, that has one very important implication, and that is that fluid expulsion is fundamentally limited by the permeability of the surrounding rocks. So that's my first assumption of 4. Okay, if we're going to study compaction, we need to choose a rheology, and there are only 3 to choose from, so it's not a really complicated task. I will assume that, as a starting point, compaction in the lower crust is viscous. And that means that the compaction rate is proportional to the total pressure difference minus the fluid pressure, or in other words, negative of the effective pressure. And I assume a constitutive relation, which gives the compaction rate then a specific form. Compaction rate that gives the compaction rate is a function of a geometric factor, which is on the order of 10, or 1/10, sorry. The coefficient of viscous flow, effective pressure raised to some stress exponent. Now, the stress exponent really doesn't matter for any of the things that I'm going to talk about, at least not in non-dimensional form. But it does matter in terms of what the mechanism of compaction actually is. And whenever I assume one mechanism, people make fun of me for not assuming the other one. And I would just like to make an argument here for mechanisms in the lower crust. Pressure solution is usually thought of as a low stress compaction mechanism, whereas dislocation creep is thought to be a high stress. So people like this pressure solution creep mechanism for the lower crust. The argument against that, or a possible argument against that, is that although compaction is a dilational deformation, it's accomplished by microscopic shear. That is, you have to grind out all the porosity by basically shearing the individual grains. So what that means is that if a rock is undergoing simultaneously shear and compaction, they must occur by the same microscopic mechanism. So since everybody likes to believe at least that shear in the lower crust is by power law creep or dislocation creep, I will assume, for the sake of dimensional arguments, that dislocation creep is the operative mechanism. So I have a nonlinear viscous rheology. Okay. If we're going to have a viscous compaction mechanism, we must have some kind of pressure difference. There must be a difference between fluid pressure and total pressure. And while shear deformation can generate those, I think for pervasive compaction, the only real way to explain that is the static pressure, the difference between the static pressure gradient between the fluid and the solid. And the main thing about the static pressure gradient is, first of all, it only develops orthogonal to the gravitational field, so in the vertical direction. And secondly, did I already say this? It's proportional to density. What that means is that if we have a fluid and solid intermingling, and you can sort of think of a slowly deforming solid being and a pore fluid being the analogy to this glass of water, both will develop their hydrostatic pressure gradients. The fluid pressure gradient will be steeper, which means less steep in this plot, which is an unfortunate thing about using depth coordinates. So that although we can have a point where we have mechanical equilibrium, that is no effective pressure, above this point the fluid must become overpressured relative to the solid, giving rise to a stress that causes dilation, whereas below the fluid is underpressured, causing compaction. And this effective pressure gradient, if these two fluids are static, is basically a constant, and it's not a very large constant. So it's 200 bars per kilometer. If we want large effective stresses, we must have significant vertical extents of hydraulic conductivity. So how do you get a significant extent of vertical hydraulic conductivity? That was answered a long time ago by Ruby and Hubbard, or a good explanation of this was given by Ruby and Hubbard. Basically, they suggested that the lower crust consists of hydraulic seals, behind which the fluid is basically compartmentalized, which would mean that we would have seals, which are at near lithostatic pressure, and then behind this, the fluid pressure gradient would become hydrostatic, and we would get this effective pressure gradient increasing below each of these seals. And that then leads to my final two assumptions for this model. The first of these assumptions, the hydraulic assumptions, the first is that permeability is a strong function of connected porosity. Typically, people assume that permeability is a cubic function of porosity, and that's justified by an enormous body of evidence, so I won't bother to try and argue it. And the second assumption, again, is fairly well established, which is Darcy's law, which says that fluid flux is proportional to permeability, or in this case, porosity raised to some power, and the fluid pressure gradient. And if you think about what Darcy's law means for a slowly compacting crustal column, which you might imagine my initial crust consists of, the divergence of the flux throughout this column will be constant, or zero. That means then that I can rearrange Darcy's law to say that the fluid pressure gradient is 1 over the porosity cubed. So the fluid pressure gradient is going to be enormously sensitive to small variations in porosity. Okay, so the final mystery for me to resolve is where the lower crust is, because I've defined the lower crust as a place where viscous compaction occurs, and that's a slightly different definition than the conventional definition of where the lower crust is. Normally, the lower crust is defined by the brittle ductile transition, which is actually defined by the crust response to tectonic stress. And the problem there is that compaction is occurring in response to a completely different stress, that is effective pressure. Fortuitously, the effective pressure and the differential stress are relatively well constrained in the upper crust by behavior of the upper crust. And it turns out that if you make very simple models for these, you find that these two stresses are comparable. If they're both comparable, we have very similar constitutive relations. They just differ by an order of magnitude. So if we know tectonic strain rates, then we also know the compaction rate at the brittle ductile transition. And if you invert this compaction rate for a time scale, what you find is that it takes 50 million years to 5 billion years to affect an order of magnitude reduction in porosity. That means that even by metamorphic standards, compaction at the brittle ductile transition is painfully slow. So, of course, the answer to that problem is to heat things up. Viscous deformation is thermally activated. Normally, this thermal activation is expressed by an Arrhenius dependence, but I'll convert this Arrhenius dependence. Have I not been talking into this microphone the whole time? Anyway, I have? Yep, we can hear you. Ah, good. That's a big relief. Or maybe not. Instead of using this temperature-dependent form, I'll use a form where I relate depth, the variation in viscosity with depth, to a length scale for variation in viscosity. And this length scale is basically determined by an algebraic relation to the Arrhenius relation. And I refer to it here as the viscous e-fold length for dislocation creep and most mechanisms other than pressure solution creep. This length scale is more or less independent of reasonable thermal estimates for reasonable thermal state, and turns out to be on the order of 1 kilometer. So basically, the viscous rheology is going to change by a factor of E over 1 kilometer's depth. That means the efficiency of compaction will increase tenfold for every 3 kilometers, or I can get 3 orders of magnitude variation, get away from this very slow compaction, by going about 10 kilometers below the brittle ductile transition. So this is my grand scheme then for the initial conditions of my metamorphic process, or metamorphic devolatilization. We have an upper regime where we have negligible compaction, what I would define as the hydrological upper crust. Then we have an area where localized compaction, something I'm not really going to pay attention to, is responsible for sealing fractures and giving rise to this famous fault valve behavior. And that sort of wanes at the brittle ductile transition at temperatures around 325 degrees. And then somewhere maybe 10 kilometers below that, we have a regime where pervasive compaction is an efficient process on a metamorphic timescale, which I would define as the hydrologic lower crust. And I would say that that basically corresponds to amphibolite facies metamorphism if you're trying to orient yourselves in metamorphic petrology. Greenschist facies metamorphism is in this transitional regime where we really don't know, can't expect to know what's going on very well. Okay, so that was sort of a model for the initial pressure. The only other thing I need to specify for my starting point is initial porosity or initial permeability, which in this model are the same thing. And I should say I'm talking about connected porosity. That's the only thing that concerns me. And I'm also for me, porosity is anything that's present on scales that are smaller than the length scale for the fluid flow. So it might, in fact, include fractures. But in any case, this property is probably very, very poorly known in the lower crust. And the only thing we can really say is that if we know that metamorphic fluxes or fluxes on a metamorphic timescale are very small, and we have a fairly good idea that they are, and we assume that these fluxes are maintained by lithostatic pressures, then we can invert permeability, invert Darcy's law for permeability, and invert this permeability for a metamorphic porosity. And the funny thing about this porosity, which is also probably completely illegible, is that it's extraordinarily small, 10 to the minus 4, so something which would be almost, would be unobservable geophysically. And it has an uncertainty which is incredibly large, plus or minus 3 orders of magnitude. And that uncertainty is not some kind of experimental uncertainty. I think that's the variability we can expect, or it's the kind of variability we would expect from the intrinsic variability of rocks, that is, the intrinsic heterogeneity of rocks. So we basically, first, we know porosity is small, it's highly variable. Metamorphic reaction can produce very large porosities, so they can make have a very large impact on hydraulic properties that depend on this porosity. Why am I so concerned about this porosity? Basically, this porosity via the compaction time and length scales, which you can deduce from dimensional analysis, these scales depend on a bunch of physical properties which we could hope one day to know, or maybe we already even know, but they're most strongly dependent on this porosity. So if we don't know this porosity, we have no way of predicting or anticipating what the hydrodynamic response of the crust is. The only way to find what these length scales and time scales are to actually observe metamorphic processes. And I'm not a big observer of metamorphic processes, but there is a set of observations that really intrigued me, and that was these were made in the early 90s, or mid-90s, mid to late 90s, when ion probes were brand new, or when I was still reading the literature. These studies attempted to time the duration of fluid-rock interaction. And the 3 studies that I read, maybe I didn't pay attention to all the others, deduced an incredibly short time scale for fluid-rock interaction, somewhere on the order of 10 to the 4 years, when the time scale for metamorphism is someplace around 10 to the 7 years. So one explanation for this very short duration of fluid-rock interaction is that reflects the time scale for compaction. Well, it's not very wise to do this, but I reparameterized the compaction length in terms of initial flux and initial porosity, which is a slightly misleading formulation. And this plot shows time scale for compaction versus length scale for compaction. And if we choose this 10 to the 4 year time scale, and we say that metamorphic fluxes are less than 10 to the minus 12, which is sort of what we expect in time integrated fluxes to be, we come up with a length scale that is less than 1 kilometer, which is conveniently observable. Okay. So it's at least, in principle, we could expect to see these compaction phenomena. Now to porosity waves. To make sort of like the simplest model I can possibly make for explaining metamorphic porosity waves, I'll assume the reaction has no dilational effects associated with it. If it has no dilational effects, it can't possibly perturb the hydraulic regime all by itself. right? The hydraulic regime only responds to pressure effects. If I have no pressure effects, there's no perturbation. And for the moment, I'll neglect shear viscosity, and I'll add a little bit to my initial crustal model. I'll add time and a heat source, and this heat source initiates a metamorphic reaction, and the reaction begins propagating upwards. So after a very short time, what you would expect to find is some reaction front, and behind it, this little region of reaction-generated porosity. Now, the important thing to realize is because this cannot possibly, the reaction can't perturb the fluid flux through this column must be unperturbed. If it all has the same flux, the only way I can have the same flux in my high porosity, high permeable region and in this low porosity, low permeable region is to relax the fluid pressure gradient. That is, the fluid pressure gradient must go towards hydrostatic conditions. And if there's no pressure effect associated with the reaction, then the point at which the fluid pressure is in mechanical equilibrium with the rock must occur in the middle of this high porosity domain. Well, that will then give rise to this dilational stresses at the top and compaction, or stresses that form, or pressures that lead to compaction at depth. But in the initial stages of reaction, the vertical extent will be small, so these will not lead to significant deformation. With time, of course, that will change. And the high pressure will drive, this dilational overpressure, if you like, this fluid overpressure, will drive hydraulic diffusion into the overlying rocks and cause dilation of the porosity above the metamorphic reaction front, at the same time as compaction squeezes the porosity at the bottom. But as long as the porosity stays in contact with this source of porosity, the vertical extent of this high porosity region will continue to grow as the reaction progresses upwards. So this porosity will translate upward at the same time as the reaction, but it's got to translate faster. And as this thing grows up, these pressure anomalies will become larger. At one point, this domain of porosity can escape from the reaction front, at which point it's isolated from the reaction front, but I still have these pressure anomalies, and that will cause this domain to propagate, which, if I were going to give you the short version of this talk, I would say is the birth of a porosity wave. And I will give you the short version, but I won't claim this is the birth of a porosity wave, because that just makes a blob of porosity. It doesn't actually make a stationary state for the porosity. That is, the porosity would dissipate with time. The interesting question is why they don't dissipate. And the answer to this turns out to have nothing to do with rheology. It's a remarkably simple phenomena. And to explain it, the explanation I like most is to consider fluid flow in an inviscid matrix. If you have an inviscid matrix, the fluid velocity is only a function of porosity. And if we had a high porosity region bounded from above by a low porosity region and connected by a ramp, it's clear the fluid behind has to catch up with the fluid in front, and this will lead to a sharpening of this porosity profile. And this sharpening will go on as long as this fluid flow is going on. So if we can make this, well, inevitably, this fluid flow will sharpen this ramp to a step. Now, once I make a step, I know that the step has to be moving faster than the fluid behind the step, or at least as fast as the fluid behind the step. But if you think in a reference frame of the step itself, the step must be catching up with the fluid in front. So the shock, or this high porosity region behind the step, must be gaining mass. But if the fluid behind is already moving at a speed I know, the only way I can explain that this shock is gaining mass is for the shock to actually propagate faster than the fluid behind, which means that this shock is going to grow faster than hydraulic diffusion can widen this porosity profile. And that's, in fact, the exact same process that's going on in the viscous case, the viscous porosity wave case. It's just that the strength of the matrix resists this tendency to form a step, and you get some other shape of the porosity distribution. But it turns out that the minimum, the condition for stability of the porosity wave in an inviscid matrix is exactly the same in a viscous matrix or an elastic matrix. It's only dependent on the porosity permeability relation. And it turns out that the speed of the shock, in order for this phenomena to occur, the speed of the shock must be the same magnitude, well, it must be the same multiple as the porosity exponent above the velocity of the fluid in the unperturbed matrix. So can we get that? Well, metamorphic reactions produce very large perturbations, so I think it's very easy for them to meet this condition for shock stability. Okay, in my youth, I was a big fan of numerical models. I am less enthusiastic about them now. But of course, numerical models, you can put all sorts of whistles and bells in. So when I started working on this problem, I put in a model with heat flow, kinetics, dilational reactions, you name it, it was in this model. And this is the result. This is, here are porosity profiles as a function of depth and time, and the pressure profile, or effective pressure anomalies associated with these porosity profiles. And I have this metamorphic reaction propagating upward in time. It's a little more diffuse than a line. And you can see that putting in all this fancy stuff does make some strange things go on at the reaction front, but that we do get these porosity waves here. And of course, all these whistles and bells make some complicated relation between effective pressure and reaction kinetics and all this other stuff. But after a little bit of time, what I realized is that these waves are basically lazy. They form with the minimum possible velocity that is necessary to escape from the metamorphic reaction. Which means, in essence, that these waves are going to carry the time average, vertically integrated fluid production. So if I know how much fluid is being produced beneath this reaction, I can say roughly how much flux has to be carried by one of these waves. So it's sort of steady state. The other thing the numeric results are fairly useful for is that they show that these waves are numerically identical to steady state solutions to the compaction equations. So if they're a steady state, it means I can formulate what these solutions should look like analytically. And what that means, in essence, is I know the dynamic permeability of the lower crust. That is, I choose a constitutive relation. I can find an analytic form for the equation of state. And then I can plot as a function of the vertically integrated fluid flux all the properties of these waves. So if you tell me you want to accommodate a certain flux, I can tell you no problem. It will be done by a certain kind of wave. There's one catch there. And that is that it's relative to the initial flux. And if you don't know this initial flux, you have no chance, basically, of describing this process. So again, it comes down to the fact that dynamic permeability is very sensitive to what the initial state of the system is. Okay. Well, as I alluded to earlier, observationally based geologists are very suspicious of people like me who sit around with pens and pencils and draw things. And this view sort of typifies that. I mean, I guess these people seriously think we're interested in modeling an idealized system. So just to show you that I'm not just interested in idealized systems, here are my considerations about heterogeneity. And to some extent, these arguments about heterogeneity also apply about heterogeneity and mean stress. There are two cases. The trivial case is that we have very large heterogeneities. If we have very large heterogeneities, the waves will just develop independently within each lithology. The more interesting case, which also shows that I'm not Cambridge educated, is little or small heterogeneities. In that case, I'm talking about heterogeneities that are much smaller than either of the compaction length scales of either of the two lithologies. And we can take the limiting case that one lithology is completely rigid and ask, well, is there a steady state possible in this system? And indeed, it turns out there is. And the reason why is it turns out that the time scale for the compaction processes are going to be much, much greater in the rigid material than in the soft material. So all we need to do to make a steady state, and I can demonstrate this numerically, is that you make the rigid material have a high enough pressure gradient to conduct the flux between the soft materials. And that means that the dynamic permeability or the dynamic response of the crust is basically determined by the weaker rheology, or the rheology with a softer compaction length. And it makes for very amusing looking porosity waves. I wish I had time to show you those numerically. Okay, well, all this stuff was, well, except for, well, pretty much all this stuff was known long before I started. And I would like now to go towards some more complexity. And the first thing to consider is flow in multidimensional matrix. The solutions I've been talking about so far are one-dimensional. That means if I have a one-dimensional high porosity source or metamorphic reaction, the waves will be sill-like structures that propagate away from the reaction front. And what was known long before I started was that these waves, these one-dimensional waves, are unstable with regard to spherical or circular and 2D porosity waves. And people like these porosity waves because they move a little bit faster. But it turns out that if you look at the analytic solutions for these, the reason these things are going faster is primarily because they just they are more effective at focusing. They do spatial focusing, whereas the 1D case are just doing temporal focusing. If you look at these waves without the noise that I've added to this system to make these two-dimensional waves, you find that they have perfect symmetry, and that their pressure distribution is an antisymmetric dipole, which means that there's a tendency for fluid circulation out of the high pressure region and into the low pressure region. Okay. Well, of course, it was very embarrassing for me not to know that there were 2- and 3-dimensional solutions to these waves. But fortunately, I can make an excuse for why I did the 1-dimensional waves. And that is the temperature effect of the crustal rheology. We expect the crust to become harder upwards. And we have basically these 2 length scales, a rheological length scale, the scale on which the viscosity of the crust is changing, and a hydrodynamical length scale, or the compaction length. And this rheological length scale is more or less fixed, around 1 kilometer. It increases slightly with depth. And this hydrodynamic length scale, or compaction length scale, is an exponential function increasing upwards of this rheological length scale. What that means is if we put a wave very far down, or a perturbation very far down, it will see a constant viscosity environment because it's so small. But as it propagates upward, it will grow in length scale, and eventually it will start to feel the upward strengthening of the crust. And when it does that, it's much like hitting a barrier. It just flattens out these two-dimensional waves. What that means is if we start out with a 1-dimensional perturbation in the lower crust and we try and perturb it, it will break up into blob-like waves. But as these waves near or rise to the upper crust, they'll tend to go back to this 1-dimensional like solution. Okay, so that story can be basically summarized by this picture. Below a certain depth, that is when the compaction length is very short compared to the rheologic length scale. We have only 1 length scale for fluid flow. When these 2 length scales become comparable, we split into 2 different length scales. One, the compaction length controls the horizontal length scale, and the rheologic length scale controls the vertical length scale. And that leads to this flattening of porosity waves. And you can expect that this is going to become very important near the brittle ductile transition. So as we get near the brittle ductile transition, we can have a very large length scale for horizontal fluid flow. The other thing is when we get in this rheologically dominated regime, the waves are going to slow down. They slow down exponentially as they rise upwards. So that means that in the absence of other rheological mechanisms, the mid-crust will act like a graveyard for lower crustal porosity waves. And this is, in fact, supported by a fair amount of geophysical evidence for sub-horizontal accumulations of fluids beneath the brittle ductile transition. Okay, so that's the end of the story for viscous compaction. What other mechanisms do we have? Can we add to this system? There are 2, basically. First, viscous waves are propagated by negative effective pressures. And if you tell anybody in rock mechanics that you want negative effective pressures to do something viscously, they'll look at you like you're insane. They basically, as soon as you have negative effective pressure, people start talking about embrittlement. And at what point that would really occur, I have no idea. But it's certainly, as we get into this transitional regime, it's got to become fairly important because there are also significant differential stresses at that level within the crust. The second thing we have to worry about, and that will be a more catastrophic transition, is in the neighborhood of the brittle ductile transition. Plastic embrittlement will result in a release of fluid pressure so that we get larger and larger positive effective pressures. And that, at some point, is going to give rise to elastic deformation mechanisms. So what I'd like to do first is consider the effect of incipient plasticity. And to sort of accommodate people in rock mechanics, as much as they hate this model, my basic idea is that we can accommodate plasticity as some kind of asymmetric viscous mechanism. That is, we have one viscosity in compaction and another one in decompaction. And my justification for that is when we have incipient plasticity, we have 2 mechanisms operating in tandem. In parallel, so a Kelvin-like rheology. One is overcoming cohesion in some subcritical manner, and the other is true viscous dilation, whereas in compaction we just have viscous compaction. And these 2 in tandem will lead to an effective viscous rheology, but with some reduced viscosity. And if we want to parameterize that, what we can say is that we want the maximum fluid overpressure to be comparable to the tensile strength of the rocks. If you do that, it's very simple to derive what the characteristic length scale for that must be. And if you go through that exercise, what you then find is that the time scale for this decompaction process must be much less than compaction. Well, the negative effective pressures within a porosity wave are always at the top of the porosity wave. And this is going to be true for any compacting system, at least as long as gravity or mean stress is decreasing upwards. So that means that this decompaction weakening basically has the opposite effect of thermal activation. It weakens rocks in the upward direction. So whereas we've already seen that strengthening in the upward direction causes flattening of porosity waves, it's intuitive that these waves if the crust becomes weaker going upwards due to plasticity, these waves are going to become elongate structures. And that's what this simulation shows. What it is the upper panels show porosity profiles where I have a high porosity layer bounded from above by a low porosity layer. And the lower diagram is the effective pressure anomalies associated with this. And here you can see these waves moving away, and behind them they're leaving a trail of uncompacted porosity that sort of channelizes subsequent fluid flow. And another curious feature about these waves is that they're actually compacting the matrix as they propagate through, something that viscous waves don't do. They're drawing fluid in, and that's because they have a very asymmetric pressure distribution where you have a very large underpressured part of the matrix, which is basically sucking fluid from the matrix as it propagates upwards. The curious thing about these waves is they form with a spacing that's is identical to the compaction length scale. I mean, it's almost numerically identical in this thing. So we have very strong spatial focusing with this rheology, characteristic spacing, and a channel width that's related to the yield stress. So if the yield stress gets very small, these waves become very, very, very sharp. I won't bother with this. Right. The next thing is lateral fluid flow. This, I sort of haven't obviously read the metamorphic literature for some time, but recently I noticed that metamorphic fluids seem to flow up and down temperature most of the time, and I really don't understand quite what that argument is. But to sort of emulate that, what I thought to try and model would be lateral flow towards a low pressure area, a drain. So if we had a metamorphic reaction taking place in a drain, and basically in that scenario, there are basically, sorry for using basically so much, two M-member scenarios. One where we either have no plasticity or very high yield stress. In this case, the reacted layer has very high porosity, and the length scale for fluid flow within this high porosity region will become basically as much larger as the porosity is over the background porosity. So we can have very large degrees of lateral fluid flow in this scenario. The trade-off on there is, of course, we lose something in the time scale. The alternative is this viscoplasticity, or this decompaction weakening I was just talking about, which implies we have very low yield strength. And it turns out that this low yield strength also reduces the time scale. So depending on these two time scales, either the decompaction weakening is going to win off, or the drainage into the long scale drainage will win the battle for fluid flow. To illustrate this case, I set these two scales equal in a numerical simulation shown here. This is a porosity profile, pressure profile, and the vertical and lateral scales for fluid flow. And this scale here is the compaction, the compaction length scale within this high porosity region generated by the metamorphic reaction. And this scale here, or this bar, is supposed to represent the compaction scale in the unperturbed matrix. And the time for this simulation is very near the initial condition, much shorter than either of the compaction time scales. And what you see is that this permanent fracture zone, which I've made to act as a drain, is draining the fluid very far away from the metamorphic reaction front. So at this point, none of the compaction mechanisms had time to react. If we go to a time interval where these are comparable to the two compaction time scales, what you see is that compaction has won, the porosity waves have won over the high porosity channeling within the layer. That is, we formed these porosity waves, tube-like porosity waves, with this characteristic spacing of the compaction length within the matrix. And the interesting thing about these waves is they have sort of a convective pattern, at least in the reference frame of the wave, which means that not only do we get very strong vertical fluxes within these waves, but we get very strong lateral fluxes within these waves. So they sort of are an interesting mechanism for metasomatism. Just to illustrate the alternative scenario, that is, we don't have any compaction whatsoever. If we put a fracture into the lower crust, it'll allow this reaction to go for a very long time. The porosity doesn't know that it's supposed to compact, so we just have this huge drain in the lower crust. And what happens is it completely draws fluid out of the rocks lying over. That is, we have a large region of downward fluid flow. So we get a completely different pattern if we neglect compaction. And what really, I think the point here about this kind of model is it has no intrinsic time or length scale. That is, in this kind of modeling, if I make a rigid model for the crust, I can make anything happen just by screwing around with the parameters of the model. So I think the reason to study compaction is it gives us these length scales and time scales, or included. Okay, so can you escape to the upper crust? Can you ignore compaction in the upper crust? The answer is no, of course not. And the reason you can't is that there are porosity wave solutions through the entire spectrum of rheology. The viscous waves are, if you imagine a fluid source, the solitary wave solution is like drops coming away from the fluid source. And that happens because the fluid pressure and the porosity are basically independent. In the other limit, the elastic matrix case, which we would expect at the brittle ductile transition and above, porosity is basically or you can map porosity to effective pressure. You lose 1 degree of freedom, and as a result, the waves cannot detach from their source. And the funny thing is, you have a non-dissipative rheology that gives a dissipative type wave, whereas in the viscous matrix, we have a dissipative rheology that gives rise to a non-dissipative wave solution. And there's a continuous spectrum between these. It turns out that as soon as you add any elasticity, you do get a dissipative solution, but they can look very much like the solitary wave solution. But yeah, okay, the interesting thing about these waves, or one interesting thing about these waves, is they can propagate through zero porosity, but I won't bother to talk about that. Rather, I'll just illustrate one case of these waves, what might happen in a upward strengthening viscoelastic crust. So the brittle ductile transition, I don't know, it should be somewhere around here. I put in a metamorphic reaction that generates high fluid pressures. And this sort of surge in porosity, which is also a surge in pressure, it reflects my initial equilibration of the system. What happens very shortly after this, and that's just like a few thousandths of a compaction timescale, is that the system adopts sort of a viscous pattern where you see these viscous waves slowly rising up to the brittle ductile transition where they get stuck and nothing much happens. And then all of a sudden at some point this elastic solution takes over and you get this surge of fluid pressure into the overlying crust. And this surge lasts literally, it's like only a thousandth of the compaction timescale. Then once it relieves the pressure and you go back to this viscous domain. And this kind of behavior has been invoked to explain things like the timing of fluid-driven aftershocks. So it is something which I think there is good evidence for in the upper crust. So you can't get away from dynamic permeability anywhere in the crust. Yeah. Metamorphic petrologists get extremely upset with me about this stuff. And they say, well, they always ask me, well, does anybody ever see a porosity wave? Well, the problem is in metamorphic petrology, nobody ever sees really anything. So I would like to sort of end or wrap up by pointing out that there are real porosity waves in nature, or accepted porosity waves in nature, but people just don't call them that so often. The first case is sedimentary basins. In sedimentary basins, we have sediments moving downward, but people believe, and I think there's fairly good evidence for this, that the porosity profile in sedimentary basins is more or less eustatic. So we have a porosity profile that stays fixed relative to the surface, and sediments moving down. So the exact opposite of what I was talking about with the metamorphic porosity wave case. It's just that the porosity is sitting towards the surface. And of course, these are of economic interest because of their potential for trapping gases or oil. The other case is at the other end of the temperature spectrum. So on either side of metamorphic petrology, we have mid-ocean ridges where everybody pretty much accepts that we have this domain, a eustatic domain of high melt-filled porosity that supplies the melt to mid-ocean ridges. And also everybody accepts that we have the mantle upwelling through this region. So here again, we have porosity staying fixed as the matrix moves through it. And I think those are, both of these are described by pretty much the same mechanics as I've used for the metamorphic porosity wave, although I doubt that persuades anybody. Okay, so conclusions. The good thing about a Bowen lecture is that you have essentially almost unlimited time. Normally, I never get to my conclusions. And as usual, so I don't really have a good set of conclusions. This is supposed to be my field area, by the way. People usually accuse me of never going in the field, but yeah, I do have a field area, and it's a very friendly place, actually. So what are my conclusions? One of my conclusions, and it's funny because every undergraduate learns this, that compaction happens. Well, if compaction happens, and especially if it's viscous, there is no possible steady-state lower crustal regime. But despite this, we have this huge spectrum of models with people assuming this, and it's really not a very good idea. Well, I don't think you learn anything by doing it. Yeah, this is kind of a trivial one. In isolation, viscous compaction leads to fluid accumulation in horizons beneath the brittle ductile transition. This is also pretty trivial, so we can skip that. And what is this one? Yeah, this is a good one, actually. I like this one. This one, yeah, so, it's fine to ignore compaction. Well, I don't like it, but you can. But when you're configuring a model for lower crustal fluid flow, you have these scales already made for you. And you should at least use them to test your hypotheses, like how long your rigid model could possibly last. So with that, I will conclude. Thank you very much for your attention.
Right, we've perhaps have a few minutes for some questions. I'll step down and again, people who want to ask questions, if they could go to the microphone so everybody can hear, that would be great. So any questions for Jamie?
Yes, I can.
I don't think you ever explained the rheology of that, or how important that might or might not be.
Well, fortunately, I was in a talk earlier this afternoon, which said that well, first of all, if it's subcritical, this fracturing is basically controlled by the rate at which fluid is driven into these fractures. So basically, the fracturing process will be limited by the rate at which viscous compaction, I assume, viscous compaction mechanisms at depth supply fluid to drive this fracturing. So as long as there's some time dependence to the process, I don't care the details of the mechanism, and as long as it's much smaller than the compaction length scale. Is that at all an answer to your question?
Maybe, but I guess I briefly thought we had a reservoir sitting in the mid-crust that might be sort of, dare I say, steady state to feed those things.
You mean my graveyard, or do you mean this graveyard is not a true steady state, because if it's accumulating, right, it's not, but it would be a slowly compacting. It would be a reservoir to drive all sorts of funny things if you want, like if you want to replenish restore high fluid pressures along a fault zone or something like this, it would do that, but it would do it on a relatively slow time scale compared to the fracturing process. But there I'm talking about fracturing or loss of cohesion deeper down with incipient plasticity. At the brittle ductile transition, these porosity waves may drive fracturing, may help to propagate fractures, but it's not the viscoplastic mechanism I'm talking about with channelization and things like that. That was probably a terrible answer, but.
Okay, other questions?
Yeah, this may not be so much a question, something that I may have missed, but you're talking, I think, quite correctly of various intrinsic, timescales to the problem. I didn't understand how the timescale of the kinetics of the metamorphic reactions come in. What's the rate at which you're generating sort of, fluid and so on, and how that impacts the problem, or are you in some limiting behavior where we can just assume an initial condition and go from there?
Yeah. There are two things. The one thing I found was that well, first of all, when you have a diffuse region of metamorphic reaction, the compaction scales become, the length scale becomes much larger within this high porosity region. So if I don't have a drain to draw fluid off, basically the only thing that I have to wait for is not the fluid production beneath this reaction zone, or within this reaction zone. I have to wait, or the mechanism that limits me is the rate at which I can pull fluid off. So my assumption is that these reactions are relatively slow on, is that correct? Slow on the time scale of the reaction generated porosity. That was reasonable.
There don't appear to be any anonymous Cambridge petrologists around. Anonymous. Right. Okay, thanks very much, Jamie, for a great talk. And just remind everybody the VGP reception is at 6:30 in Salon 9 in the Marriott. And both Jamie and Marc will be receiving the Bowen Awards at that ceremony. And we've also given the award of the Kuno medal as well. So, sorry, the Kuno Award as well. So we'll hopefully see you all at in the Marriott in just over half an hour.